Well, pre-calculus classes, we're getting down to the end of the school year, so not too many more of these sets of notes, but good morning, good afternoon, or good evening as always. For 10.5, last section we cover, there's two parts. First part has a little more to it than the second part, which is actually pretty quick, but we're going to talk about the binomial theorem, which I know in past years you may or may not have seen this with Algebra 2 a little bit. When you work with the probability unit, some years your teachers get to this, some years they don't. So again, you may or may not have seen some of this, but what we're going to talk about with the binomial theorem, and then on the next page, we're going to actually talk about what we're going to fill in here initially comes from what's known as Pascal's triangle. Now, we're going to use throughout most of section 10.5 what are known as binomial expansions. Now, when you have a binomial expansion, basically that's just saying, we're working with all of these as, x plus y, so whichever power, that'd be like taking x plus y times x plus y times x plus y, and so on. Now, as long as you're not actually multiplying too many of these out, that's really not that big of a deal. Now, of course, the first one's really easy. X plus y to the 0 is just 1, because anything to the 0 power is 1. I know as we've even worked through working with the especially geometric sequences, geometric series, you're working with that 0 power a little bit, but x plus y to the 0 is 1. X plus y to the first is x plus y. Now, if we take x plus y to the second, there is going to be an x squared. There will be an xy plus another xy, so 2xy. And then at the end, there will be a y squared. Now, for these remaining ones, like I said, we are going to fill these in. And then as we go through the next page of notes, I'm going to actually come back and explain where these come from. But if you have x plus y to the third, that is x to the third plus 3x squared y plus 3xy squared plus y to the third. Now, again, this one wouldn't have been that bad had we actually asked you to multiply these three out. Again, it really starts getting tedious, though, after the second expansion. Now, x plus y to the fourth is x to the fourth plus 4x to the third y. Then the next one is plus 6x to the second, y to the second. The next term is plus 4x y to the third, and then the last term is plus y to the fourth. Now, there are some patterns you may already see emerging. Powers go 3, 2, 1, and then technically 0, 4, 3, 2, 1, 0. The powers of y go up. 0, 1, 2, 3, 0, 1, 2, 3, 4. Well, the next one is x to the fifth plus the next term is always whatever the exponent is, 5, x to the fourth y. Then the next one is 10, x to the third y to the second. Then the next one is also 10, x to the second, y to the third. And then at the end, it's just going to mirror 5x y to the fourth, and then at the very end, y to the fifth. Now, like I said, there is some symmetry here. The degree of each term is x plus y to the n power, meaning power of 5, 4 and 1 is 5, 3 and 2 is 5, 2 and 3 is 5, 1 and 4 is 5, or 5 is that fifth power. Now, these coefficients, where these come from, is if you take x to the n minus r power, y to the r power, where basically what we're saying is as you go, each power here is, this is the nth power, and then whatever you're subtracting by as you go is that r. Now, That is what's known as a NCR. This is a combination. There is a formula on your calculator for doing this. The actual formula is n factorial divided by r factorial times n minus r factorial. Now again, depending on what you've seen with Algebra 2, if you've done the probability unit, depending on what, your teachers were able to cover, this n factorial, if we use like an actual number, for instance, 7 factorial. Now, it doesn't mean someone's just excited about the number 7's like their favorite number. It's not 7 exclamation point. What this means is 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, again, your calculator has that as an option. You enter in whichever number you want, and then math, and then you go over to probability down to the exclamation point, and it's 5040. So again, it saves you from actually doing that again. This is also one of those formulas if you go back into that probability. So we will actually use this here at various points. Now, to talk a little more about where these come from, there is something known as Pascal's triangle. Now, Pascal's triangle technically, and I know it's going to sound kind of odd, but it technically has a row 0. Row 0 is at the top, starts with 1. Then row 1 has 1 and 1. Then row 2, again, you just keep going down diagonally. Then the next term, I take and add up these two numbers, and then there's a 1 on the outside. Well, here is, if I can get these so they show up. There's your 1, 1x plus 1y. 1x squared, 2xy, 1y squared. Well, row 3, there is a 1 on the outside, then 3, add those 3, and 1. Well, let me actually fold this over. We have x to the third, 3x squared y, 3xy squared, 1y, or y to the third. So as I was actually multiplying these out, I mean, technically, yeah, I kind of know these in my head. As long as you have the first one, you can keep expanding them out. So row 4 is 1, 4, 6, 4, 1. And then that row 5 is, again, kind of try to position it diagonally. 1 and 4 is 5, 4 and 6 is 10, 6 and 4 is 10, 4 and 1 is 5, and 1. So if I want x plus 1 to the third, I am going to use row 3. So I'm going to have 1, 3, 3, 1. Now, here's my Pascal's triangle row. Well, what I'm going to do is I take this first one, it's x to the third times 1 to the 0, plus, so this is the x, this is now kind of like in place of the y, plus 3x to the second times, and then 1 to the first, plus 3 is my coefficient, x to the first times 1 to the second. Now I realize as you're using 1, you don't actually have to use these values in there, but that's how these all work. And so, again, here is my x and y. As I go down the list, I am just moving down by 1, moving up by 1. And then at the end, plus, since it's a 1, x to the 0 times 1 to the third. Well, what does this give us in the end? X to the third times 1 to the 0, x to the third, plus 3x squared times, since it's 1 to the first is just 1, plus 3x plus x to the 0 is 1, times 1 to the third is 1. So that's x plus 1 to the third. You can do this for any binomial expansion. Again, if it's a third power, you could almost argue, okay, what's easier, this or, just multiplying it out directly. As you start getting into, though, 2x plus 3 to the fourth, this is where I'm going to argue it is a little easier using the row of the triangle. So if it's row 4 or to the fourth, I'm going to do 1, 4, 6, 4, and 1. Now, again, these are the coefficients to start. It's up to you, especially when there is a 1, that's this one, that's this one. You don't necessarily need to write those now. When there are coefficients of x, or your variable, that's where you do have to be a little careful. It is 2x to the fourth times 3 to the 0, plus 4 2x to the third times 3 to the first, plus 6, here's where I didn't quite space these out well, 2x to the second, 3 to the second, plus 4 times 2x to the first, 3 to the third. Now again, do you need to actually write in some of these powers? No. I'll leave up to you just what you need to write down. I just like to, especially as we get started, show all of these patterns. And then 2x to the 0 times 3 to the fourth. So from here, well, 2 to the fourth is 16, x to the fourth. Plus, you have a 4. There is a 2 to the third times 3. Is 96, x to the third. Now here is where some of the numerical symmetry starts going away. Then the next one, you have 6 times 2 to the second times 3 to the second. Now I'll leave that up to you. If the numbers are easy enough, you can actually just write those down and, multiply the numbers directly. So 6 times 4 times 9 is, let's try that again, 6 times 4 times 9 is 216, x squared. Then we have 4 times 2 times 3 to the third, which is 27, so it's 8 times 27, 216 as well. So plus 216x. You can see all of my powers are still decreasing. And then at the end, well, this is just 1 times 3 to the fourth is 81. So there is 2x plus 3 to the fourth. One thing that we have not yet talked about is, okay, what happens if we throw in a negative, and we'll talk about that. Well, the way that works is, so again, we're still going to use 1, 4, 6, 4, and 1. You're still using that row of your triangle. Well, it's going to be 2x to the fourth, and then negative 3 to the 0. If there is a minus, we're going to treat it as a negative. Plus 4, 2x to the third, negative 3 to the first. Plus 4, 2x to the second, negative 3 to the second. Or, sorry, that should be a 6. Then 4, 2x to the first, negative 3 to the third, and then at the end, 2x to the 0 and negative 3 to the fourth. And then we'll just, again, expand that out. Well, 2 to the fourth is still that 16x to the fourth. Now, anything to the 0 is 0. The only thing that changes as we go from 2x minus 3 from the last problem, 2x plus 3, well, if you take negative 3 to the first, that's going to be negative 3. So the last term, everything is the same from our last example, except it's minus 96x to the third. So sometimes the question is, how does the minus come into play? Well, just as you're expanding it, treat that second term as a negative number. Then the next one, because when you take negative 3 and square it, it's positive 9. Well, it's 6 times 4 times 9, which is still plus 216x squared. Then negative 3 to the third, that is negative 27 times 8 is minus 216x plus negative 3 to the fourth is positive 81. So again, the only change from example 2 is plus minus. Again, the plus stays, plus minus plus. So these signs will alternate if it's minus, positive, negative, positive, negative, positive. If it's 2x plus 3, everything's going to be positive. All right, one final example. For day 1, 5x minus 2y to the fifth. Now we'll even talk about, okay, what happens if we have a variable in both terms, which can happen. So again, go to your triangle, and this one I'm going to 1, 5, 10, 10, 5, and 1. Maybe a little more space. So we start out 5x to the fifth, negative 2y to the 0, plus 5 times 5x to the fourth, negative 2y to the first, plus 10, 5x to the third. These numbers, I will tell you right now, are going to get a little ugly. Minus 2y to the second, plus 10, 5x squared, negative 2y to the third, plus 5 times 5x to the first, negative 2y to the fourth, and then plus, out here at the end, 5x to the 0, and negative 2y to the fifth. So, like I said, going to be kind of an ugly, set of things to work through here. Well, first off, 5 to the fifth, 3,125, x to the fifth. This is where you do not want to actually do the expansion individually with separate parentheses. I mean, this is kind of ugly as it is. Then we have 5 times 5 to the fourth, and then times negative 2, negative 6,250, x to the fourth, y. Then we have 10 times 5 to the third times negative 2 squared. So 10 times 125 times 4. If you know numbers off the top of your head, certainly use those. 5,000, x to the third, y squared. Then 10 times 5 squared times negative 2 to the third. So 10 times 25 times negative 8. Negative 2,000, x to the second, y to the third, and then we have 5 times negative 2 to the fourth. So 25 times 16, I believe is 400. X, y to the fourth. And then out at the very end, we have negative 2 to the fifth, negative 32. And then you can just look at your power pattern, y to the fifth. So that is 5x minus 2y to the fifth. Again, we're just using that row of Pascal's triangle that's needed. You can certainly even just to come back here, one final finishing. If you want row 6, you just can keep going. 6, 15, 20, 15, 6, and 1. Or, doesn't take real long, I've got a little bit of space here. 1, 7, 21, 35, 35, 21, 7, and 1. So you can obviously keep going with it. Now, for day 2, we'll even come back and talk how it works, because needless to say, we're not going to ask you to do an expansion of all the terms beyond row 5. But that wraps up at least the first part of section 10.5.